Okay, so today we're going to continue on with exercise 3A. We're going to go through a couple of old exam questions that point to this is probably as complex as maths methods will get. Okay, so we're going to go through some of the hardest stuff. So this is a good example of to indicate what you can expect when it comes around to the exam. So we're going to go through what we call a conjecture problem. All right, and so that word, hopefully you've sort of heard of it before, but when we come up to it, I'll sort of explain in a bit more detail what it means. Now, let's just first say, with this kind of question, the most important thing for you to do is get as many marks as you can. All right, so it's often difficult to get all of them. Ideally, you want to get all of them, but the main thing is get as many marks as you can. That's always the case, come test, come exam. So yeah, conjecture problem, we'll read through it. I'm going to show you a few things on the calculator, how we can use the calculator to help us out. With this problem, I wouldn't expect you to be able to look at it and solve it right now. Okay? You've got all of the skills you need, but you haven't had any exposure to these kinds of questions. Okay? So I have a whole booklet of these kinds of questions. It's going to be something that we keep looking at again and again, building up confidence and competency in this particular type of question. They pop up in like 60% of exams, right? They're a pretty common type of question, so we need to make sure we're getting good at it. So we're going to read through the question. With conjecture problems, you generally have sort of three types. They're either about tangents and normals. Okay, we've just done tangents and normals, so it's a suitable time for us to cover it. Or they're about turning points, maximum and minimums, or the other one is integration, which is we'll do later in term 2. Okay, so let's read the question. Consider the function f of x equals k plus k on x, where k is greater than 0. So we're not even told this number k. The graph is shown below when k equals 1. So what does that mean? It means they've graphed the function 1 plus 1 on x. 1 on x, not 1 on k. Alright, so they've changed the value of k to be 1. Here's the graph. Part A. Estimate the, so I'll keep reading it. The tangent and the normal to the graph when x is 1 are also shown. So we should look at that and go, when x is 1, let's look at that point there. There's the tangent, okay, it's parallel to the curve. You can see my mouse moving along, that's the tangent, and there's the normal. Okay, so that's what it says. Then it says, estimate the x coordinate of the point where the normal to the curve intersects the graph again. So here's the normal. Where does it intersect the graph again? Here. And it says, what's the x value of that point? Okay? And the answer is x is minus 1. Alright, so for part A, we're just going to write x is minus 1. Alright, so we're just reading off the graph. We're saying, where's the normal intersect the graph again? Now, they've graphed it for k is 2. So they've graphed the function 2 plus 2 on x. And they've got the normal drawn there for us as well. And they're asking the same thing. They're saying, for the function shown below, the tangent and normal when x is 1. So we're continuously drawing the tangent and normal when x is 1. This time it says, where does the normal meet the graph again? Where does the normal meet the graph? This time it's x is, and it's what's the closest integer value? Minus 4. Okay? So for part B, we're going to answer x is minus 4. Alright, on to part C. For the function k plus k on x when k is 3. So that means we're considering the function 3 plus 3 on x. Right? We've changed the value of k to 3. The normal of the graph at x equals 1 has this equation. So they've given us the equation of the normal, and it's in general form, right? They've given us x take 3y equals minus 17. Okay. Find the x coordinate of the point where the normal intersects the graph again. So they're saying, when does this normal meet this function? So first I'm going to demonstrate an algebraic process, and then I'm going to show you how we can use our calculator to just G-solve it. Now this is in general form, and unfortunately on the calculator there's no setting to graph a line in general form, which means we just first need to rearrange it. We need to get y by itself. We need to get it in y-intercept form. So we'll subtract x from both sides, and then we'll divide both sides by minus 3. X on 3. Alright, so y-intercept form, I'm going to write it like this even actually. Y equals a third x, so you can see what's n? N is a third, and the y-intercept is 17 on 3. That's the equation of the normal to this curve at the point x is 1, okay? So if we're trying to find it algebraically, we're saying when does this function meet this function? And functions meet each other when they're equal to one another. This is the y value, this is the y value. When are they equal? It's when this is true. 3 plus 3 on x equals 1 on 3x plus 17 on 3. Now we can go through and do the algebra there. We'll actually do it in a moment when we do the general case. For now, all right, if we're going to use our calculators, we're going to graph this function, we're going to graph this function, and we're going to g-solve the point of intersection between them. So let's pull out our calculators. I'm going to use decimals, but I will use my calculator as well. And what is it? 1 on 3x. So what we want to be doing is going into graph mode and sketching both functions. So the first one is 3 plus 3 on x. And the second one is I've got the old, it's so annoying this thing. X on 3 plus 17. Alright, so you can see it. So you've drafted. And what we're asked is we're saying, what's the x coordinate where they meet, where the normal meets the curve again? So on your calculator, what you're going to do is you're going to press G-solve and intersection. And that's going to bring up the 2 points for us. G-solve, intersection. And we can see one of them is minus 9. That's where it meets the curve again. And the other one we've got is positive 1. That's where we've drawn the normal. We've drawn the normal at x is 1. And it meets the function again at x is minus 9. So the solution to part C then, all they're looking for is this statement. Alright? It's only worth 2 marks, so you're not required to perform the complex algebra involved in solving that manually. In an exam, it's very clear when they want you to find an answer using exact methods. Alright? It says find the exact solution. Alright? Here, we can rely on our calculator to help us out. So, are there any questions at this stage? Alright, so next I'm going to draw the table that we've got there. So, the table is this one here. It says, using your results from parts A and B and C, fill in the table. And so we've got K and X coordinate where it meets the curve again. And so we saw when K was 1, the X coordinate was minus 1. When K was 2, it was minus 4. Right, that's from part B. And then from part C, we saw when K was 3, it was minus 9. Alright, so that's filling in the table. And these conjecture problems always follow the same suit. They always start with specific case 1. Specific case 2, we've got inductive evidence to infer a general conclusion, to make a conjecture about what's this pattern we're observing here. What's the link between these numbers? Alright, so it says, on the basis of these results, the following incomplete conjecture is made. Alright, so they've stated it for us All right, so conjecture is like a mathematical guess. I've got good evidence to suppose this is true, all right, albeit it's only inductive evidence. I'm going to prove it deductively in a moment. For the function k plus k on x, the normal to the graph of y equals f of x at the point when x is 1 intersects the graph again at a single point, and the x coordinate of that single point is, what do we know is here, the x coordinate. If we have here k, all right, if we have here, here's k, what's going to be the x coordinate? What's
negative k squared.
Very good, well done, John. Yep. So you can see here, this number, it's negative, but then it's squared, isn't it? 2 squared is negative 4, 3 squared, and then it becomes negative 3 squared. So our solution is, if we have the function k, the general case, we expect the x coordinate to be negative k squared. Okay, so that's quite tricky to see, and some of them do get a little bit more trickier than that. Nonetheless, if you don't get this part, you can still move on to the next part. So let's turn the page. Look at this. Prove or disprove your conjecture. Oof, 6 marks. All right. So I've said we want to get as many of these marks as possible. So I'm going to point out what we're always going to be doing. So they always start the same, right? Specific case, make a conjecture. All right, now we have to prove the general case. We're going to prove that it's true for all values of k. We can't just prove it for another value of k because that just adds more inductive evidence. We want it to be true deductively. So, prove the conjecture. Let's think, what are we trying to prove here? We're trying to prove that the function k plus k on x, okay, that the normal to this function, normal at x is 1, we're always doing the normal at x is 1, all right, meets the function again when x is minus k squared. So that means we need to start with those things. We need to say, here's the function. What is the equation of the normal to this function when x is 1? That's our first step. Okay? So if we want to find the equation of a normal or a tangent, we always need 2 things, right? We need the point of contact. Okay? For the point of contact, we're talking about x is 1. When x is 1, the y value is going to be k plus k on top of 1, k plus k, it's going to be 2k. We've got the point of contact. We're well and truly on our way to finding the normal. Okay, so we've got the point of contact. What else do we need for a normal? We need the slope. All right, so we need the slope. We need the slope when x is 1, and then we need to perform the negative reciprocal, right? Because we're doing a normal, not a tangent. So here's the function. We need to find the derivative. So firstly, I'm going to write the function like this. It is k plus kx to the minus 1. X is our variable, right? K is just a number. And so when we differentiate this, k is going to disappear. And we've got minus kx to the minus 2. Or minus k on top of x squared. Which means the slope when x is 1. All right, remember we're talking about the normal when x is 1. If we put x is 1 in here, all right, I'm going to make the argument like this. F dash of 1 is going to equal minus k on 1 squared, which is minus k. So that's the slope of the curve, but we need the slope of the normal. So we need to perform the negative reciprocal of this. And so therefore the slope of our normal is 1 on top of that. Alright, so that's probably 2 marks so far. That's a third of the marks. Okay, to get our next mark we need to find the equation of the normal. Alright, so it's got these properties. What is a normal? It's the equation of a line. Here's its slope. Here's its point of contact. We've got everything we need. And it's confusing because we don't have numbers, we've got these letters. Doesn't matter. They operate the same. We treat them as if they are numbers. So we're looking for the equation of a line. All right, y equals mx plus c. It has a slope of 1 on k. And it passes through this point. When x is 1, y is 2k. So let's substitute that in. We're going to put the 2k where the y is. One on k times 1 is just 1 on k. All right, and then to get c by itself, we'll subtract 1 on k from both sides. So we have c is 2k, take away 1 on k. All right, so all of that is to say the equation of the normal then is 1 on kx plus 2k take 1 on k. Y equals mx, the slope is 1 on k, the y-intercept of the normal is 2k take 1 on k. Alright, so it's pretty complex, right? Pretty complex. So we're 3 marks, we're halfway. Alright. Now, what are we trying to prove here? What we've done so far is we've found the normal to this function at x is 1. This is the normal. And we're trying to prove that when the normal meets the curve again, the x value is minus k squared. So we're going to say, well, when does this normal meet this function? So we're going to equate them, and now we're going to perform that algebra. Now I might do that over here, so we've got a bit of room. So we're saying, when does the normal 1 on k x plus 2k take 1 on k, when does the normal meet the curve? Right, this is what we're trying to solve. What are the x values that make this true? So what we're doing when we're trying to solve an equation, we want to get the x's on one side, the numbers on the other. We want to try and solve it, right? So that's what we're just trying to break it down to isolate x. So that's what I'm going to do. I'm going to keep this here. I'm going to bring this term across, and I'm going to put both of those numbers over on that side. I'm going to put the numbers on one side, the x's on the other. All right, for now. Now from here, there's lots of different ways of doing it. Okay, and the more we process it, the closer and closer and closer we're going to get to an answer. So I'm just going to show you the way I did it this morning. All right, I was practicing this morning, so yeah, I remember how to do this. So x is on one side, so let's move this term over first. So we're going to have 1 on kx take k on x. All right, so I'll move the first term over. And then I'm going to move these numbers over that side. So we're going to have k take 2k plus 1 on k. Alright, so I've got the k's on one side and the x's, everything involving an x on this side. Now, I might even just express this, rather than being 1 on k times x, I'm going to express it as x on k. That's fine. Alright, so then we want to start collecting like terms. We want to bring these together, okay? That's what we want to do. We want to bring things together so we can simplify it, right? So what I'm going to do here is I'm going to multiply this term by x on x, and I'm going to multiply this term by k on k. We're cross-multiplying, right? We're multiplying by 1, we're not changing its value. So let's just focus on the left-hand side for now. We're going to get x squared, take k squared, over the same, they've got the same denominator, which means that's an operation we can perform, we can bring them together, over xk. Alright? On the right-hand side, we've got k take away 2k, minus k plus 1k. Alright, same deal. We're going to try and bring those together. Alright, let's focus on the right side now. We want to try and bring those together. So I'm going to multiply this term by k on top of k. Alright, so maybe I should use a different colour as well. So we just keep hacking away at it, keep breaking it down, keep trying to put it in a form that's useful to us. So I'm going to multiply the first term by k on k. Multiplying by 1, not changing its value. What do we got? We've got minus k squared plus 1 on top of k. And I'll rewrite the left-hand side so we can see. Okay. So keep going, keep trying to break it down. Now that we've got this, all right, now that we've got the x's on one side, the numbers on the other, let's get rid of the denominators. Okay, let's try and eliminate the denominators to simplify the equation. So I can see I've got k as a denominator on both sides. If I multiply both sides by k, all right, it's going to cancel. All right, k is at the top here and then, and same here, that's cancelled. All right, so we can do anything to an equation as long as we do it to both sides, right? Multiply both sides by k, that's a legit operation. Okay? But we've still got this x at the bottom, and we want to get rid of that. We want to eliminate that x somehow. So I'm just going to keep going and keep rewriting what we've got. We've got x squared take k squared on top of x equals minus k squared plus 1. Now we're going to multiply both sides by x. It allows us to get rid of the denominator, right? So I'm multiplying here by x and here by x as well. Now this is useful insofar as we've eliminated the denominator there. So we've got x squared take k squared is equal to, and here the x is just going to distribute. What do we have? I'm going to write like this, x take x k squared. Alright, x times 1, x times minus k squared, minus xk squared. Right. And we're looking at that and we're saying, oh, gee, I'm not really seeing much of a solution here. And so this is where it requires sort of maths teacher level insight that you guys are going to develop over the course of these conjecture problems. What we want to do is we're going to bring everything to the same side. Okay? So I'm going to come up here and I'm just going to bring everything to one side so we can apply the null factor law. So I'll take away x plus xk squared equals 0. So all I've done, moved that over, we're all on one side. And we're going to look to see if we can find a solution. Alright, now I can actually see a couple of ways of doing it even from here. So, which one's going to be the most simple? What I'm going to do next is put the k terms next to each other and the x terms next to each other. So I'm just going to rearrange the terms, okay? The only important thing is that I keep whether it's negative or positive belonging with it. So I'll put xk squared first, and then I'm going to put minus k squared next. Alright, so that term's first, then I've got minus k squared, then I'm going to have plus x squared, this one, and then I'm going to have take x. Okay, so I've just rearranged it. That's fine. Then what we're going to do is we're going to say, I can actually factorize this. Okay, so I'm looking at that. I'm just looking at these first two terms. What's common to these first two terms? K squared. All right, so I can express the first two terms like this. X take 1. All right, if you just look at the first two terms, and we were to distribute k squared, we've got what we have at the top. And then if we look at the second two terms, what can I factorize? X. Okay. Now what's common to both terms? X minus 1. Okay, that's coming out the front. All right, you can see the solution. Null factor law. It's a beautiful proof, hey? What a monster to get through though. 6 marks. So, a couple of things to say. Firstly, QED, Latin quod errata demonstratum, it has been demonstrated, we've proved it. Null factor law, we're familiar with that. Can anyone tell me, why do I have two solutions? Why do I have x is 1 and x is minus k squared?
Because it's when x is 1.
It's because of the normal, very good. So if we look at the graph of either of them, all right? Okay, the x is 1 is where we drew the normal. What's this question we've answered here? We've said, when does the normal meet the curve? Well, of course it meets at x is 1 because that's where we drew the normal from. That's the solution we expect. And here we've proved that x is minus k squared is the other solution. Okay, so I want to console you. Don't be overwhelmed by these problems. All right, it's not something I would just hand you and say, here, have a go at this. All right, it's something we're going to develop and build up to. And again, it's just about getting as many marks as you can. You definitely want to get the earlier marks, the specific case, all right? Understand the questions. See if you can see the conjecture. And even in the circumstance where you can't see the relationship, I've rubbed out the table now, but where you can't see the relationship between x and k, that doesn't matter, because you can go ahead and prove it, and this is your answer, and then you can go back and fill the box in if you get to that stage, all right? So they're tricky problems. What I want us to do is turn the page and have a go at the next one. All right, so this one's a little bit easier. This one requires you to do it in general form, okay? And that's a hint that's given to you because it presents the question in general form. Because everything's presented in general form, don't bother trying to rearrange it. Deal with it in general form. Demonstrate your competency in general form. So let's spend the next, before recess, going over that, having a bit of a go at that, and we might go through an answer a little bit after. Don't be overwhelmed. It's fun.